Hello, welcome to Laboratory in Physics 2 course. In this video, I'm going to show you how to perform the L3 experiment, which is about the polarization of light. So, before we're going to start, we should know the objectives of this experiment. First, to study the polarization of light by refraction, by shine the light through this acrylic glass. And then the second, we're going to use the Snell and also the Buster law to find the refraction index of this acrylic glass. Before we go further to the experiment part, let me briefly tell you about the theory of polarization. To understand what the polarization of light is, we first need to know what the light is made of. Generally, the light is referred to a visible light, but it could actually be any kind of light, both visible or invisible, such as infrared, UV, or even X-ray. They are all basically electromagnetic waves, which is composed of electric and magnetic fields, denoted as E and B field in the figure. These fields oscillate perpendicular to each other and propagate in the same direction with the speed of light. The concept of polarization is related to the oscillation of electric field because the light we see in the nature is composed of a number of electromagnetic waves. We can guess that the electric field of each wave oscillate in various planes as shown in figure A. For example, this one, and this one, and this one. And that means this kind of light is regarded as unpolar light. Moreover, the light will be completely polarized if the oscillation planes of all the electric field are the same as shown in figure B. In some cases, the light can also be partially polarized if most of the electric field oscillate along nearly the same direction, like this one. And this is called partially polarized. To produce the polarized light, one can let the light passing through the polarization filter, also called polarizer. So all the electric field will be filtered by the polarizer, except the one that oscillate in the same plane to the transmission axis of the polarizer. According to the Malus law, the intensity of the filter light is reduced to a half of its original intensity, and it won't change no matter how we rotate the transmission axis. When we observe the polarized light through another polarizer, we'll see the light with different intensity depending on the angle between polarization plane and the transmission axis of the polarizer. According to this equation, you may notice that once this angle is 90 degrees, the intensity of polarized light will become zero, because cos 90 degrees is zero, right? So I2 becomes zero. And what that means is the intensity of polarized light will become zero. In the case of partial polarization, the intensity of light will change to some extent, but it won't be zero. Among several ways to produce the polarized light, this experiment is relevant to polarization by reflection. Based on Malus' observation, it states that when an unpolarized light beam is reflected from a surface at a particular angle of incidence, the reflected light can be completely linearly polarized, and this angle will be called the polarizing angle. And based on this observation, Buster found that the maximum polarization of light may be achieved when the angle between the reflected ray in a medium and the reflected ray is 90 degrees. Referring to Snell's law, which describe a relation between the refractive index and the angles of incidence, which is theta 1, and the angles of refractions, which is theta 2. We can replace theta 2 as a function of theta p in this figure, and this can be done by consider the relation between these three angles. So we know that the summation of these three angles should be 180 degrees, right? So we got this. So one can write theta 2 as a function of 90 degrees subtracted by theta p. So we got this equation, and from this, and this function will become cosine theta p, and from this we just move cosine theta p to this side of equation, and we obtain the tangent of incident angle is equal to the ratio between the refractive index n2 and n1. And if the light initially moves from the air to another medium, we get n1 equal 1, right? And then we will get a simple equation like this, where the theta p is called Brewster angle. In this experiment, as we want to find the refractive index of this material, which is acrylic glass, we first need to know the polarizing angle. To do that, we have to adjust the incident angle until the reflected light become polarized. And once you get a polarizing angle, you need to draw a Ray diagram like this one and measure the angles given in the figure, and also write down those angles right direction and point A, B, C, D, E in the diagram as well. To measure an angle, one may use an app on mobile phone such as angle meter or protractor, which are available in Play Store and App Store. Or you may print out the diagram and use protractor to measure angles. Then you calculate the refractive index of acrylic glass by using Snell and Brewster laws. And to do that, we need these two equations. And then calculate the percentage difference between the refractive index obtained from those two laws. And that's all. Now we're going to the experimental part. About the equipment in this experiment. First, we have the light source which produce red light shining through a single slit in front, so that we get the light beam out of the light source, and make sure that it connected to the power supply. And the second is a rectangular acrylic glass. The third, which is very important, it is a polarizer, and there is a Polaroid here, and we can rotate like this to change the plane of polarization of this Polaroid. And we have this one, protractor, and we use this to measure the angle between each light beam. And also we have several pins, and we use this to fix the paper on the foam plate, and also to mark the position of the acrylic glass that we're going to place on the A4 paper, and also use it to mark the direction of the light beam, so that we can draw the line and then we can measure the angle. And that would be all equipment we need in this experiment. To perform this experiment, first we have to set up the table like this. What I mean is, we have to put the foam plate like this and place a paper A4 here, and also the acrylic glass. To make sure that anything won't move, we just use the pin to fix the paper with the foam sheet by pin it at the corner, each corner of the paper, like this. Okay, I think 3 corner one. So I think 3 corner would be enough. And what is next? We draw the line to mark the position of this acrylic glass. So I do this. Okay, this would be enough. And next, we're going to connect the light source with the power supply and turn it on and shine the light beam into the acrylic glass that we already marked. And at this point, if we turn the light off in the room, we will see the reflected light and reflected light. And the one that we're going to check whether it is polarized light or not is a reflected light. To verify if the reflected light is polarized light or not, we use the polarizer. And to do that, we just rotate. And when we rotate this one, what change is the plane of polarization or Polaroid will change. And if we adjust the right angle, when we rotate like this, we will see the dark light. What I mean is, when you see the reflected light, at first it's bright. But as you rotating this, what change is the brightness of the reflected light will change. And when we see nothing, the brightness of the reflected light become 0 or it's become dark. That means the reflected light become polarized at that point. And to find the right angle that can produce the polarized reflected light, we have to change the angle that the light beam acting on the acrylic glass. To do that, we have to gradually change the angle like this. Then we have to check if it is polarized light already or not. If not, we change the angle again, and then we check the type of polarized light by using this polar line. And once you get the angle that can produce the polarized reflected light, we use pins to mark each light beam on the paper, and then we remove them all and draw the line on the paper, then use the protractor to measure the angle. After that, we use the Snell and Webster law to determine the refraction index of the acrylic glass. And that's all for this experiment.